What if there were no rules in F1? How fast could the cars go? What would the engineers change? And could the drivers actually survive? F1 or motorsport with no rules is something that engineers dream about, and the questions have been asked before. But there must be some rules. There must be somewhere for the driver to sit, there must be four wheels, the laws of physics must be followed, and the cars must be optimised for a lap time around a Formula 1 circuit, like Silverstone or Spa. So before we get into how we developed a no rules car and how fast it might go, let's take a minute to look at what's been dreamt up already. First up, the Volkswagen ID.R Pikes Peak, a 671 horsepower electric motored monster that owns the fastest time up the legendary Pikes Peak hill climb at 7 minutes and 57 seconds. Yes, the car is extremely fast. It has to be to have the record at Pikes Peak, but it's still a bit overweight at 1100 kilograms and ultimately is not 100% focused on aerodynamic performance, as described here by the very aerodynamic looking head of exterior design.
Car has to look juicy, nice, sexy, desirable, and that's our job. You know, aerodynamic, of course, is something important, but the design is at the end. This is what matters.
Then we have the Porsche 919 Evo, which is what happens when Porsche's engineers take an already very successful race car and then rip up the rulebook. It has more downforce from a flatter front nose, a wider rear wing, and a larger diffuser. And while we're talking about aero, it also was able to move parts to generate more downforce and then remove drag, apparently generating 50% more downforce than a 919 race car. Engineers also added lightness by removing about 40 kilograms by getting rid of non-essential parts like headlights and onboard jacks. The car was also able to use more fuel and therefore had more power, getting up to 1160 horsepower. But still, it only had a tiny 2-litre V4 engine, and I'm sure if that were changed, there'd be even more power available. And then we have the brainchildren of Adrian Newey, and probably the designs that we have to take the most seriously for this video. Whether Volkswagen had to look good and be all corporate, and the Porsche was an adaptation of an existing race car, Red Bull's X2010 and X2014 are purely focused on lap time. Granted, they'll likely never be built, but they have been designed from zero, with speed around a racetrack being the North Star. The first X2010 concept uses a forced induction 1480 horsepower engine that theoretically could achieve a top speed of 292 miles an hour and a maximum lateral turning load of 6G.
I mean, the car looks very cool, first of all, but you know, it's very good to drive as well.
But Newey, being an engineer, thought he could do better and decided to add a fan to the car to help the grip in the low and medium speed corners, where there isn't enough air flowing over the car for it to create the downforce itself. This is something that AMZ Racing focused on with their car that broke the 0 to 100 kilometers an hour world record, accelerating to 100 kph in less than a second, which I just made a video about. So, in theory at least, the Newey car should be able to do 310 miles an hour and pull 8G on the brakes. That's around 3G more than a modern F1 car. But one of the key things here is that Newey's car only weighs 545 kilograms compared to the 800 kilograms F1 cars are today, and the slimness F1 cars haven't been since the early 90s. Now, of course, this car was for the Gran Turismo game, and I'm unsure of how credible the numbers actually are, but the aerodynamic concept is the important thing here, and if that has come from Newey, we probably should take note. What you might not know is that a no-rules formula has actually existed in real life in the past. It was called CanAm, and it produced some of the most awesome cars ever.
The CanAm series at Road Atlanta, featuring the fastest racing cars in the world with the largest racing engines in use anywhere.
CanAm, or the Canadian American Challenge Cup, was a racing series from 1966 to 1975. The regulations were minimal to say the least. Unlimited engine sizes, including allowing turbos and superchargers, and virtually unrestricted aerodynamics. It's basically the closest that any major racing series ever got to having no rules. As long as the cars had 2 seats, wheels enclosed by bodywork, and met some 1970s safety standards, you were good to go. As you might imagine, this allowed engineers to come up with some genius solutions and push racing car development more than ever before. CanAm cars were some of the first racing cars to have wings, turbocharging that actually worked, ground effect aerodynamics, and aerospace materials like titanium, all of which are commonplace in motorsport today. It really was a development bed for engineers, and that's what I love. But unfortunately, as you might imagine, all this development led to rising costs and the eventual downfall of the series. However, there was a period where CanAm cars were often as fast, if not faster, than the Formula 1 cars of the time. So, with all this freedom, what kind of cars did CanAm produce? Well, the first mention goes to the Porsche 917 30KL from 1972. And this thing was an absolute monster. A 5.4 litre flat 12, 1100 horsepower in race trim, and there's more. It actually produced 1580 horsepower in qualifying trim. Just look at how much fun this car must have been. Eventually though, the Porsche was restricted, with regulators enforcing a fuel consumption rule for 1974. However, like with the 919 Evo, Porsche then used the car to break some records, with it breaking the closed course speed world record at 221 miles an hour at Talladega Speedway, and it reached 240 miles an hour on the straights.
Mark Donohue established a new world record mark at Alabama, 221.160 miles per hour.
CanAm can also be thanked for bringing ground effects into motorsport with the Chaparral 2J. Now, you've probably seen this weird looking car before, famous as it had a massive fan on the back, but I'll leave it to Sir Sterling Moss and the designer Jim Hall to explain the technical side.
This is the fan that helps suck the car downwards. What's this plastic skirt?
Well, the skirt's a seal to maintain the vacuum under the car. It's made of Lexan, so it'll stand a 200-mile-an-hour impact.
This was groundbreaking. It had two fans adapted from a military tank driven by a two-stroke engine. And who doesn't like tanks and a two-stroke? The 2J competed in the 1970 season and qualified at least 2 seconds quicker than the next car, but being rather complex, it did break quite a lot. And unfortunately, it was again outlawed by the organisers, but the concept did manage to make its way into Formula 1, with Bernie Ecclestone's Brabham team and the Gordon Murray designed BT46B. Speaking of engineering genius, if you'd like to start your journey to becoming the next Adrian Newey, you should check out today's sponsor, Brilliant.org. Brilliant is the best way to learn more about engineering that doesn't take years of schooling. It's free and easy to understand. They're the best way to learn maths, data science and computer science interactively. Brilliant is built for busy people. You can learn anywhere, anytime on your phone, tablet or computer and master big concepts in as little as 15 minutes a day. And so their bite-sized lessons make it easy to build a daily habit. There are over 100 courses with thousands of lessons and new content added monthly, so you can stay up to date with the latest concepts behind world-changing technology. So if you want to try everything Brilliant has to offer for free for 30 days, then visit brilliant.org/driver61 or click on the link in the description. The first 200 of you will get 20% off Brilliant's annual premium subscription. So we've decided to take on this project, but where do we focus our attention? Well, there are 5 main areas to work on: aerodynamics, power, weight reduction, tyres and suspension. Now, there's a lot of improvement we can make, but for the scope of this video, I'm going to focus on the big one: aero, and maybe I'll follow up with another video about what's possible with the engine and the tyres. Now, the overall goal is to create a car with more downforce and less drag. More downforce means later braking, higher cornering speeds and better traction. Less drag means we can go faster on the straight bits. So how should we approach this? Should the car look like an F1 car, or more like a prototype car? Or should it just be a big vacuum cleaner like the 2J from earlier? And does it need to have lots of pointy bits like a 2008 F1 car, or does it need to be smooth and rounded like the Volkswagen ID.R? Well, I recently had Willem Toer on the Drive61 podcast to help me understand more. And first, he explained a little bit about F1's aero rules.
The aerodynamic rules are also quite restrictive. You have CAD files you have to follow where you're allowed bodywork in a certain zone. If they took those dimensional restrictions away, you would be able to add quite a significant amount of organic downforce to give you more aerodynamic power.
So basically, F1 forced designers to work within a set of predefined areas, and they can't go outside of these. Therefore, the basic shape of an F1 car is defined by the rule makers. And before we complain too much, there is an important reason. The engineers want to make a fast car, of course, but the other thing they want to do is keep other cars behind them. And if there weren't any regulations, they'd do their very best to create a massive hole in the air behind their car, so the cars behind have very little downforce. And no one wants to watch racing where there's actually very little racing. But what would we actually focus on, aerodynamically speaking, on our no rules car? Well, of course, we'd need to work on the typical areas: the front wing, the side pods, the floor and the rear wing. But with no rules, there's much more that we can work on. We could use active aero, wings and aero parts that move. It also doesn't need to be open top like we have it in F1. It doesn't even need to be open wheeled. And fans, we could use fans like we see in the AMZ racing car and the McMurtry Spearling. But the important thing about aero is that it all needs to work together. There's no point adding a load of downforce to the front wing if it disrupts the air flowing down the rest of the car. So let's start at the front and work our way through the car before we get to the more crazy additions. And remember, all of this is hypothetical.
Aerodynamicists around the world are still understanding and evolving the theory of aerodynamics. It's deliciously complicated.
So, the front wing. It would want to be massive in depth, something like you'd find on the Empire Wraith, only a bit bigger. But you'd only want the wing to be bigger on its edges and not that large in the middle. That way you're not making the air work too hard before it goes underneath the floor. We want all that air to be moving cleanly under the car through the diffuser, as that will create a lot of downforce. That's why we saw high noses develop in F1, starting with the Tyrrell 019 and being most prominent with the F1 cars from about 2010, before rules changed to lower the noses. But the main point of these high noses and basic middle sections of the front wing was to keep the air tidy for best use under the floor. Then for our no rules car, the outside of the wing would look similar to the front wings we saw in F1 in 2018, but maybe not quite as complex. And then we have the wheels. With regards to aero, wheels are a pain. They're exposed elements that disrupt the airflow around the car. Unlike the smooth, controllable surfaces on the car's body, wheels and tyres generate complex, turbulent airflows that can reduce overall aerodynamic efficiency. And so it's better if we just cover them up.
Fairings in front of the wheels, fairings behind the wheels. The wheels would not be truly exposed.
As with Newey's X 2014, the wheels would be covered in a fairing to ensure that the airflow is kept under control. But remember, we also need to cool the brakes, so Williams suggests a non-rotating wheel cover so that some air can pass over the brake disc and pads, cool them down and then exit in a specific place where the air can then be used down the rest of the car, so the floor. And this is where things get more simple and also a little bit more complicated. If there were no rules, the shape of the floor would actually be quite simple.
If you just focus on getting the best aerodynamic shape, which is a simple, smooth shape.
But we can only have that simple shape if the car's ride height is always perfect. And today's F1 cars do change ride height, dropping at the front under braking, squatting at the rear under acceleration, rolling in the corners, and lowering overall as downforce increases. And that's why we see a more complicated floor design in F1, because engineers have to deal with all of this movement. But we have no rules, and so we're simply going to opt for active suspension that keeps the car in the perfect attitude at all times. And there's more. We'll also have vortex generators at the front of the floor, as they can help us eke out a bit more downforce by adding energy to the air.
Rolling up a vortex means you get some higher velocity air, and where you've sped the air up locally, the pressures on that high speed section are a little bit lower, and so you can use that to get a little bit more downforce out of the air.
Oh, and I almost forgot. Of course, we'd use skirts. Skirts do the best job of sealing the sides of the floor, although they can never do it perfectly. With less air leaking in, there's lower pressure under the back of the floor, and so more downforce and grip. And finally, let's talk about the rear wing, before we get onto the active aero, the fans and the closed cockpit. First off, you'd want the rear wing to be as wide as possible, wider than current F1 rules allow. This is because the wider it is, the less angle you need to run to get the same amount of downforce, and that means less drag. Like with the X 2014, it's multi-element and wouldn't be the same shape all the way across. And this bit is really interesting. If you look at the X 2014, you see the outer parts of the wing have more angle than the central part. And this, again, is because aero all needs to work together. Just think about the air. It moves over the top of the car and then hits the rear wing before connecting again with the air coming from under the floor. That means that you'd be better off using the middle part of the wing to reduce pressure behind the floor, and make the floor even more powerful. So, of course, we already use wings and floors in F1, but what about really exploring no rules? Well, first we'd go with a closed cockpit, as it gives a smoother surface and better control over the airflow down the rest of the car. It also gives you a stronger structure, which means that the engineers would actually just make it lighter and end up having the same strength. Then we'd have active aero. Movable wings. Of course, this means that you could add wing in the braking zones and corners and remove it on the straights. You'd also add a movable device in the diffuser that would open at high speeds. So then it could have less drag and improved top speed. But one of the main benefits of active aero is that the tyres would be more likely to survive going this quickly. We haven't spoken about the engine, but imagine that a car with no rules might be able to do 400 or even 500 kilometers an hour. The tyres are going to be a weak point, especially with loads of downforce squashing them into the ground, let alone the speed ripping them apart. At least with active aero, the floor and wings could reduce load at high speed and give the tyres a bit of a rest. Okay, so what about fans?
Honestly, if there are no limits, fans.
Fans are the cheat code because natural aerodynamics only work when the car has air moving over it. So, natural aero doesn't work from a standing start and is much less effective in slower corners. If you suck the car to the ground with a powered fan, you don't need to be moving to create downforce, just like the Chaparral 2J from earlier. Now, Willem tells me that in theory, with a fan, you can create 10 tons of force for every square metre of surface. But of course, that's only in theory. You still need to find a fan powerful enough to do that, and there would be leakages, so we couldn't even get close to a vacuum.
So getting to, let's say, 30% of a vacuum, I would say should be achievable.
And if we were using fans, the design of the entire car would likely change. With fans, you can put the suction exactly where you want it and could change the handling balance of the car really quickly. For example, if you turn it into a corner and have some understeer, you could just turn up the fan at the front. However, as the car's speed increases, you'd probably rely more on the floor and the wings. The reason is that the fans might simply run out of capacity. They likely wouldn't be able to remove enough air to create enough suction while the car is moving quickly. And this is where we'd need to do more research. But it's safe to say that if there were no rules, fans would be used in some way. In fact, there are a number of Formula student teams running fans on their car currently, so it'll be interesting to see how they develop. So, we've got our car sorted, but would it work on the circuit? Well, probably not. It's been estimated that the Red Bull X 2014 could pull up to 8G. And so that causes a couple of issues. No tyre in the world could work with double the downforce of a current F1 car and a 500 km/h top speed. So there'd need to be a ton of development and a load of money spent there, even if it was possible. And then, of course, there's the driver. I've only experienced the heady heights of 8G in a crash, not sustained through a sequence of corners like Eau Rouge. And yes, fighter pilots experience up to 8 or 9G for sustained periods, but that's head-to-toe G-force, not lateral. So it can be combated with a G-suit. But I think it's safe to say that the driver would struggle with driving a full race stint with the heights of 8G. By the way, when researching this, I found out that you sneeze at 2.9G. So the next time you have a cold, like I do now, remember that you're experiencing the same G-force as Hamilton when he's turning into Brooklands at Silverstone. So how much faster would our no rules car be? In all honesty, I don't know. It would require a lot more work and simulation to find out. But for now, the closest thing we have is a lap around the Nürburgring in the X 2014 on Gran Turismo. So what do you think? How much faster could this car be? And are there any ideas that I've missed out? Please let me know in the comments. This car may be hypothetical, but fans have been used on a car to make it accelerate from 0 to 100 km/h in less than a second. I spoke to the team leader of AMZ Racing and made a video about it just here. Thank you very much for watching, and I'll see you next time.